In this screencast today we are going to talk about Prop Design FFR, which is an aircraft propeller design and optimization tool developed by FFR Engineering. My name is Felix Frischmann from FFR Engineering, and the code we are going to talk about is also based on an original code by Anthony Falzone, which is called Prop Design, and the link can be found also in this presentation. Let's talk about the original Prop Design code. As I said, it's developed by Anthony Falzone, who was doing a great job on this code to optimize and perform design tasks on Propeller. It is open source and public domain. It can be utilized for axial flow fans and a whole variety of different fans like prop fans, open rotors, turbofans, and so on and so on. It allows you to make a performance analysis and generate performance plots, and it also has a CID bridge for the propeller models generated within this propeller design tool. So what we were doing already for quite a while, and this will be now the upcoming pre-beta release of the software, which then will follow very soon in the first release of our software, is that we took the very good code by Anthony Falzone and basically made some modifications and some wrappers. First of all, we decided to transform the code in a modern Fortran way, so Fortran 90, 2003, also maybe 2008. It is partially object oriented, and we work now more with the idea of modules. So the original code was written in Fortran 77, and we decided it's time to give the code a new code style in modern Fortran. Also, I personally changed some of the build environments and the infrastructure, for example introducing CMake and some testing tools. And most of all, we decided to give the code a graphical user interface and decided to use the cross-platform Qt development tool for that, the Qt UI tool. We decided that having a graphical user interface could be quite neat for such a tool. I mean, it is in the end an engineering tool, so we all know we engineers also like to work on the console and run our applications from the console. Nevertheless, sometimes it's nice to get fast into a code to have a graphical user interface giving you some guidance through the code. Also, we decided to improve the cut and come interaction tools. Therefore, we introduced the Open Cascade GeoKernel for prop design, which allows to directly exchange cut models with different tools. Who is we? We is FFR Engineering. In particular, it's my friend and colleague Laszlo Kodela and myself, so two members of our company who decided to work on this code and modernize a little bit some parts of this code. So what is the architecture like? We have still the original kernel more or less from Prop Design, so those of you who know already the original kernel from Prop Design will recognize also from our source code the kernel features written in Fortran. In this kernel features we have adjusted little things, but the overall workflow is supposed to be the same. And then we introduced the C interface, which allows us to link to our geometry kernel and geometry tools, which are written in C++ and using Open Cascade, the open geometry library. And thus, having a C++ interface, we could write a GUI using Qt and C++. We are basically pretty much, I would say, experts in Qt and C++ and Open Cascade. So from this point of view, we decided to go this way. Furthermore, we plan or partially already tested some interaction with CID and COM tools. For example, maybe it might be ANSYS for FEAs or finite element analysis. Having such an interface allows you to link to various different tools. We will talk about that also later within this presentation. So what are really the kernel features? It is important for you to know, for those who don't know the original Prop Design software, that this is a very fast and efficient semi-analytical design and optimization tool. Yeah, so the kernel propeller design modules are basically, as I said, taken from the original code. We just ported them to modern Fortran. So I will heavily link to the user manual by Anthony Falzone for more references about the real features of the kernel itself. We focus really more until now on the wrapper around and making this also usable, for example, in C, C++, and the graphical interface. What this code is really doing, or what you are probably doing if you use such a propeller design software, is that you have a design task, a final goal. It is always important, of course, to know what you aim for and to see if the software you might be using is capable of performing such tasks. So your final goal might be to find a propeller shape, but you are aiming for actually the cold shape. So the cold shape is the shape you could produce. So for example, you could have a link to production tools like CNC, and the cold shape would be the geometric shape you could transport to your production machines and then produce it. What you actually also are interested is the hot shape, so-called hot shape. Why is that? Well, the hot shape is the shape under the aerodynamic deformation. So you have loads on your propeller, and these loads, of course, are linked to a deflection and deformation of your propeller, and this is the hot shape. And the hot shape actually is determining the aerodynamic performance, because of course the propeller performance issues are important under the real loading, under the real aerodynamic loading. And here comes the prop design. The prop design really gives you the hot shape of the propeller. If you are aiming for the cold shape, you also have to use other tools, for example, finite element analysis in combination with the hot shape obtained from prop design to have a cold shape for production, for example. There's a quite nice screencast by Anthony Falzone on that. I will refer you to, again, the material on his webpage. Now, what are the different modules in this prop design? You already saw them on the architectural overview. Namely, there are several modules, but there are in particular 4 modules I will talk about. This is the analysis module. The analysis module is really the basic analysis task. So it is determining or computing the propeller performance, and it's doing that in a semi-analytical way. And I will also have a little bit of a theory wrap-up to show you what is going on in this analysis module. Then you have the maps module. The other modules like maps, opt, and XYZ is partially using or reusing the analysis features. What maps is doing is to generate maps, performance maps like propeller performance coefficients, mass flow rates, and so on, which can be visualized in a visualization tool, for example GNU-plot. This is very neat for the engineer to have a real fast, intuitive map to see where how the propeller is performing. Then there's an opt module. This is actually a design, tasks, and optimization module. So given an operation condition, for example the velocity you aim for in your aircraft vehicle, then you can find with this opt module the optimal propeller parameters for this given operation conditions. This is of course quite neat for you as a designer of propellers. And then you have the XYZ module, which could be seen like the bridge to CAD models. So from there you can get data which could be used for CAD models. Yeah, some little wrap up on theory. As I said, I will make it very, very basic, very short, very rough. I'm also not really the big expert on all those theoretical things, so feel free to make comments if I was mistaken somewhere. Basically, I'm trying to tell you how I see the things going on in the code, and also more important, I will show you where to find further information on that. Most likely, I guess, people using such software are familiar with a lot of the theory, probably even more than I am, so yeah, I will keep that short and simple. Just I want to show you what we are doing and what we are not doing. So from the ingredients, as I said, we're using a semi-analytical method. So it is a numerical method for swept propeller geometry. And this is based on thin airfoil theory, vortex sheet modeling, panel methods, and applies the Biot-Savart law, the Kuta-Joukowski theory. For those of you being familiar with aerodynamics and also aerospace and aircraft engineering, I think these things are quite known. And what we don't do in this code actually is that we don't rely upon momentum theory, which means that we don't actually use or solve something like the Euler equation or Navier-Stokes equation or Boltzmann methods or lattice-Boltzmann methods or something like that. Of course, I know this is very popular to do for aerodynamics, to have a computational fluid code, a CFD code, and run numerical methods like CFD, like solving Navier-Stokes, to find the propeller performance. But you also know that this can be a quite tedious task, and the results often depend heavily on, for example, your model and also your mesh quality, on the mesh sizes, especially in the boundary layers around your airfoil. And very often the also advantages of having such a momentum theory based equation or system like CFD are erased by not taking care of flaws in your computation, from having bad ratios in some of your elements and the boundary layer and so on and so on. In this method, which we use here on the opposite, we have a really nice semi-analytical method which we also solve on a numerical or on a discrete system, so we solve it numerically, and thus we are actually really fast. And Anthony Falzone and also the other people publishing information on that could show that this is also still very precise, and very clear also from the methodology regarding what you are doing. Here is some reference literature, especially really for the basics. You can have a look at something like the Aerodynamics for Engineering Students, quite a nice book. And also, very important, a paper which is called Numerical Determination of Circulation for a Swept Propeller, which is really the, I would say, basis for this code. So the theory given there is really used also in this code, not directly, with some modifications by Anthony Falzone. But if you read through this paper, you will recognize also in the code which we produce here, or which we transformed into modern Fortran, what is going on and what we do. And I will really show you just the basic idea exactly of this paper in combination with some of the graphs which I actually took from the book above, from the aerodynamics book. So about limitations and assumptions, we have some assumptions on the fluid, like incompressible, rotational. And as I said, it's about thin airfoil theory, so it means that the airfoil has to be thin compared to the camber line length. And as stated by Anthony Falzone, you can use this theory, or this implementation actually of what is given there, for many things, but you cannot really apply it at the current state and the current implementation for counter-rotating propellers, tilt rotators, helicopters and quadcopters, marine propellers, wind turbines and some other stuff. So for those things you would really have to adjust something, or also some parts of the theory are complicated to be applied on those issues. Some really basic things. What are you doing? So I think for most of you this is probably too basic. We talk about, for example, the lift, or we are really interested in the propeller performance, or for example the lift of the propeller induced by the propeller, and therefore we have some well-known principles, like for example the Kuta condition or the Kuta theorem. And here I just put some plots actually from a cylinder in a flow, and then if you put some rotation on the cylinder, you can basically see that you introduce some lift. And this method could be used, for example, on such a Flettner rotor to see that if you have there a circulation, then actually you have a lift. And this is really a relation of lift and circulation, so keep that in mind, the Kuta theorem. Now you could go on and actually transform the cylinder into an airfoil shape, and doing that also the flow pattern around the airfoil, which was before a flow pattern around the cylinder, is transformed. And you see some things which make you again understand something about this lift and circulation. So What we actually aim for is something on the right lower corner where we have a flow pattern where the flow separates really or is really not separating from the airfoil, and you have here the trailing edge, so this is the back of the airfoil where the flow is, so to say, separating from the airfoil. And you have a condition that the flow velocity from above and from below is the same, and actually the circulation at this point is 0, which is not the case for the other graphs here, where you have either no circulation or too high circulation or low circulation. So if you have no circulation, then here you would have something like also a circulation on the trailing edge. And yeah, this is something which is either not really physical, so you would have some vortices here or some turbulence also there, or also something which you don't aim for. So you see that the separation point SA is actually somewhere else, not on the trailing edge. And I think you can also understand that principle if you look at, for example, airplanes doing some acrobatic flight operations, like the sport of airplane acrobatics, where you really increase or where you have a plane really increasing too much on purpose, and then you have a stall, and basically, the blades of the plane are not introducing any lift anymore, and the airplane almost falls like a stone until it stabilizes again from getting speed from falling down, so to say, and from the stream or the velocity going again around the airfoil. The airplane might stabilize, and then if it's a good pilot, he can bring the plane back into the normal flight position. The problem here is, of course, that in this operation you have a lot of forces acting on the wings, so it can easily be that the airplane breaks if this is not an airplane made for such a thing. And in the acrobatics, of course, you do it on purpose because it looks really cool. It also feels very cool if you are inside. I had the pleasure to be already several times doing acrobatics, and it's really very, very cool. You really feel also the forces acting on the wings there. And there sometimes you have the smoke over the wings to visualize what's going on, and there you can really see how the flow suddenly separates and you suddenly have some turbulences going on there. So of course there's a big relation between the angle of attack and the flow pattern. So if you have the wrong angle of attack and you really increase a lot or you incline a lot with your plane, then it's not possible to have a suitable flow pattern around your airfoil, and you basically have a separation from the thin airfoil and everything goes crazy. So this is not what you aim for, of course, and especially not for the propeller. So what you aim for is a flow pattern like this one here. And to end up here, you really need the right amount of circulation. And what people sometimes do is this vortex sheet modeling. So they take the airfoil and basically replace it by looking only on the camber line, which is also here, and then assuming that you have a discrete number of vortices. So these vortices are replacing the whole cross-section of the airfoil, and then the circulation can be determined by line integral here over the camber line and the vortices. So this is really the basic idea of vortex sheet modeling. And you have some more ingredients like the Biot-Savart law, which we'll see in a second, and also the bound vortex theory, which basically states that you have either closed loops of these vortices, which you see here. So it cannot be that it just end end like that, at a dead end. So either they connect within your flow, which you observe, or if it's not the case, they have to leave your flow, and then they're like a outward boundary condition. And you can also see that in practice, for example, on an airplane, an airport, when a big jet is landing, that sometimes later you have again some vortex coming in suddenly. So the airplane is already gone, and suddenly you have such a wave coming in vortex, and this is basically then here the back connection again of that one. So of course it doesn't look so perfect, because you have also some contractions of vortices or something going on here. It's not so sharp as it's drawn here. It's an idealized case, but it's suitable for the theory here. And then from the Biot-Savart law, actually, which is also known from electromagnetism, you have the relation that if you have a point in space here given x, y, and distance and the direction to the set of vortices, or let me start from somewhere else. You might know the Biot-Savart law by looking only at one vertex in like a singular point, but here we have a sample of vortices, and basically this is what you have to do here is that also then you look at the contribution of each of those vortices for the velocity field at the point of observation. Yeah? So each of them has an influence here, and the influence can be determined by a formula where you basically have a point in space, and you have again the line integral here over the Campbell line with the vortices, and you have something here which you recognize from the Biot-Savart law, and you have then something like the distance which is depending on your position and also here on the line coordinate system. So here the coordinate system on this Campbell line, and here you have the delta S, and also you have a direction vector. You have to think of a right hand rule. So if you have there vortices, what it's the direction which is inducing at the point of observation can be determined by the right hand rule, and of course this is also depending on the position of the vortices which you look at, and also on the position you are, so the point of observation. So this one is quite important for the following theory. And you can plug that all together to make something like a panel method. So here you end up really with some discretized system, which you can then of course solve numerically. So what you are doing is that you look at the whole wing now, so not at a certain airfoil anymore, but at the whole wing. And for the whole wing, you basically have a finite set of airfoils, and each airfoil is considered to be a vortex sheet. And then here you have the trailing edge, and from here leaves this bound vortex. And this is like the trailing vortex wake, so this is the wake. And then along the wake, you also take discrete points where you can evaluate the velocity field. So this is then really the discretized system used in the numerical solution. If you look at the wing, you can see that actually along the wing, the circulation is not constant, but it's also a distribution, which makes sense. And now we go to the propeller. And for the propeller, you have to consider that, of course, the geometry is much more complex. Here you look in this paper, so this is really based on this paper, which was stated before, that you look on one of the blades of the propeller, and you look here on the chord line, the quarter chord line. And then again, you can make the same trick that you place here numerically or in a discrete system cross sections of your airfoils on this wing. And if you look at the wake, so here from the trailing edge, the vortex from the trailing edge, if you look at the wake, then of course it will be something like a helix. So not anymore here like a flat thing going in the stream direction or opposite to the direction of the airplane. And here you have something like a helix, of course, because your propeller is like a screw which is screwing into the air. And this makes, of course, things a lot more complicated, but you can derive their formulas, and this is done in this paper. And the method which is proposed there, which is turns out to be quite stable, is the following: that you have a iterative solution applying always the Biot-Savart law and also the Kutta-Joukowski theorem, because both of them are giving you relations for the velocity field and the circulation and the angle of attack alpha I. So what you can do is that in the first step you make a guess exactly on those values, so on the circulation and on the induced trailing angle. And then you use this Biot-Savart law, which is stated here, I just copied that from the paper, where you basically can compute the velocity field But you have the problem that this is only a relation, so it cannot be computed, because also on the right hand side you have the dependency on the values actually you aim for. So this gives you only a relation, but if you make a guess on the circulation and the alpha I, then you can plug them in here and basically can compute the velocity field. And then you use the second relation, which is given by the Kuta-Joukowski theorem, which also gives you a relation between the circulation and the velocity field, especially because here, and this is the trick, you're using NACA profiles. So you know the NACA profiles are certain profiles for the cross sections or the airfoil cross sections. And so from them you get actually the lift. So the lift is, you find in tables. And because you have the lift, you can use the Kuta-Joukowski theorem to actually compute the unknown, which is in this case then the circulation. And now you can compare, and also the other variables you have to compute, and then you can compare if what you guessed is what you get from those two relations. And if this is not the case, you can make a convergence loop to actually find the real values, and this turned out to be a real stable thing. And this is what's going on actually in the analysis module of prop design. Exactly that, with some modifications. So for example, in the original paper it stated that you cannot have wake contractions, so you really have those vortexes from the trailing edge remaining bounded there like a line, but in reality this is not the case, so they are turning to be unsharp, you have some turbulences, and so on and so on and so on. And this is not considered in the paper. Anthony Falzone states in his code that he considered the effect as well, and the effect is minimal, but it's also partially considered in his implementation. Yeah, this is only the analysis module. So the other modules, for example, are then using parts of that Propeller performance computation to make optimization tasks, for example, determining how many blades you should use for the given velocity of the airplane or of the airplane, so on. Yeah, this is it from the theory. I hope I explained it more or less clearly and I didn't make any mistakes. As I said, don't be too strict on me. I'm not actually a big expert on those formulas. And yeah, what we really did here now, which was our main task, is now to make the software and especially the graphical user interface, which are quite tedious tasks. And I will present you now some casted demo of the software, of the features, the handling, the utilization, and the look and feel. It is now pre-beta, so later if you release it really as a solution you can use, there might be still some significant changes in the kernel or UI. And of course, what we do here is to tell you that we are working on that. And if you have active feedback concerning the features or the UI or the handling, it is really more than welcome. Don't feel shy at all. Okay, let's jump right into the live demo of the software at the current, I would say, pre-beta stage. So I started already the software. It is a small Qt-based UI. It is multi-project, which means you can basically open several projects at the same time. But okay, this is for now not so important. I want to demonstrate you now how in principle it works, what is the basic concept of the UI, and some details of the utilization. As I said, we tried to recover this modular concept of prop design from the presentation. You might remember the different modules like opt, analysis, maps, and XYZ. These are the, I would say, important modules of prop design. There are some more in the original code, but at a certain time, at the current state, we have those modules here incorporated in the current state of the software. So let's start from the angle of view if you are an user of the, I would say, existing prop design code. So that means that you are used to have text input files and you have the different executables for each of those modules. So now here in the UI we try to unify this concept and have a UI for all different modules, but you can still run them separately, and also you can still work with your text-based settings files for the different runs. This is in general, I think, a good concept because we are all engineers, so we like to work with text files. That allows us to save some settings or maybe you have a different file format like XML. At the moment we have text file based settings saving, and thus it allows you later to run some simulation again. So you have here in the UI the different modules, so the opt module, the analysis, the maps, and the XYZ for each of the modules. And you also have the general settings. You can, for example, here hide and visualize the console with the different logging features. You also have a small help button in case you need help and want to contact us. So this is the general part. And then for each of the modules, you basically, if you click on one of them, let's say the op module, you have here a small dot widget opening, and you have here a specialized page for the module itself. First of all, you have here a small quick help, which is not really filled yet with a lot of content, but when the software will be released, there will be quick documentation to show you what to do in the specific modules. And also you have here an additional logging window. In this logging window you will see later the logging coming from the Fortran kernel for the module while running. So down here you have the general logging features, warning and error messages, and here you have the specific logic and error messages regarding the running, for example, optimization kernel or analysis kernel. And then you have different modes. So for example, here you can select that you want to run an opt run. I will actually start from a different module, let's say the maps module. So remember, in the maps module we can visualize and print the performance maps. And here we have actually more selection options because we have basically three types. You can either read in maps, and reading in maps means that you read in text files for the maps which, for example, were generated previously, or which could be also generated from the old existing prop design kernel from Anthony Falzone. So here we try to be compatible. That might be interesting. So or you might have seen that you can use GNU-plot to visualize these maps. And now with our software, you can also use our software, and you can directly use also still the old maps and visualize them. Then you have a solo run, which means you want to run only the maps module itself. So isolated view on only the maps module with the given settings. Let's go here. You see that then you have here basically some settings. You have here the abbreviations as used in prop design, and if you hover over here you get some tips. And basically the settings you have here can be also found in the existing documentation of prop design, and also I will show you some examples, for example from maps. Here these are examples provided by Anthony Falzone, and you can, for example, open here simply that in a text file, and you see that you have here in a text-based way some settings, also with the comments what those settings mean, and basically we represented that here in the UI so that you can also change your stuff here. And you can always actually also read existing input files. So let's say I opened here at the moment this input file for the Airbus A400M example, and I can go and can basically read in this existing input file, and here you saw that some things were changed such that you simply read in the input file. This allows you to really reuse old computations you did already with prop design. And then you have a third mode, which means something from pipeline, and here it's written that at the moment you cannot use that because you have to run an opt first. I will show this in a second. So again, let's go maybe step by step through the module. If you read in, you have here a whole bunch of different files which you can select to be visualized, but you also have something like a convenient auto read in button. If you use this button, what you basically do is scanning a folder and taking all the files which conform to one of the plots in this folder, so you don't have to click here manually through there. So let's do that. In the repository, which you later will be able to check out, you have also some testing output, and this output I will use at the moment for you to show what's going on. So about the performance maps, there's a folder with, for example, the A400 plots. So these are documents generated from the kernel, and yeah, now you can visualize them using gnuplot, but you can also use our software, and basically we read in all the files, and then you can trigger plot maps. And you see here, and then let's close that so that you have a better view. You see here how the maps are plotted. So for example, the mass flow rate for the two different input files, and for the different pitches or shaft power comparison, and so on and so forth. Sometimes you have also the possibility to change the units, but not here for the maps which you read in, but I will show you in a different way how that works. And now you saw, this is now basically visualizing existing files, but now you want to, of course, visualize something which you computed, and we will do that actually later in a pipeline, and I will explain what a pipeline is. Let's jump to another module, the XYZ. I told you this is kind of the bridge for the bridge for the CID model, and here you have the same. You also have three different possibilities. So reading in existing XYZ. Again, this is interesting if you have previous computed something and you have written out some text file, and here you have the same trick. You can, for example, scan a whole folder, like here in this case. Yeah, I will also use this example, and we fill in for you the different files, and you can now trigger really the drawing of the cut model. So you see here we use our CID kernel to plot the different trailing edges, the quarter chord edge, and also the one airfoil cross section at the beginning. And you can, for example, also trigger sweep faces. Then you generate a phase model. I will change here to a shaded view, and basically, yeah, you have different views on the model, so from different perspectives, and you can also rotate here around. And you see, I mean, the visual settings most likely will change, so that you can probably add some transparencies and stuff. But for now, for the demonstration, you will see this is one of the plates of the propeller, and this is now the read-in mode. And as I said, you can also run the kernel itself. Again, the same here. You have the solo run. You have some input parameters, yeah, and those input parameters are basically described in the user manual. For example, you can also check here that you have, for example, 11 number of plates, and you can again read in some existing stuff. So that means you can, for example, what could we do? Let me see. We can read in something provided with prop design. Let's say, I think that might be an interesting example. And you see here, now you get here in the module logging some information that XYZ started running and finished. Here don't get much information for this module, it's also very fast. And then you can draw the curves for this model. This takes a second of time. And you see here, we have, for example, such a model generated now really from the given input here. And I will change again to shaded view. Now you see, if we generate something from the kernel and don't read in existing files, we have two differences. First of all, you can here generate the full model, so with all the plates. And also, you might have seen before that we are generating really at each of the sampling points the cross section, and then we can use that to generate a sweep model. The sweep model might not be of highest precision. You can look through some of the screencasts from Anthony Falzone, and there he also explains that sometimes you can have problems with this sweeping or techniques, and you have to really check if your model is precise enough. We also have to work still on that, but in principle, you see, we want to generate directly a cut model, and you're always able to, for example, export this cut model in step or IGES format, and then you can use it, for example, in Rhino, in a Rhino software or any other CID software. So now we will actually do something different. We will make an optimization run. So this is now the engineering pipeline. You know what your airplane should do and how, for example, some operation conditions are. So for example, here, if you look at the opt module, you know that you have a certain velocity. Let's change something here maybe, which you want to gain, and maybe some radius. Some other settings like allow sweeping. I will just play around now a bit. And basically these are your operation conditions. And now you run the optimization kernel of prop design. And you can run this as a single module, but you can also say that you run this as a pipeline. That means that opt gives you as an output input to the other modules. I will do that, and you are warned that this will override existing input. Let's say yes. And then we start the running, and you see here something is going on. Now you see already more logging happening. And as I said, basically here you're using, for example, the analysis kernel to determine the performance of the propeller within your optimization. So actually I think now in this cast I won't even trigger the computing of the analysis module itself, because there you don't see so much except the text output. But I mean, you have to believe that what is happening there to compute the performance of the propeller is really based on this theory which I presented in the presentation, and this theory is happening in the analysis module, and the other modules are partially taking using or utilizing this analysis features. Now we are using them in an optimization run. This takes a second, so I will pause the cast and then we'll be back as soon as this has finished running. So we are finished with the optimization run. As you can see here in the log messages, the current run is the optimal design under the given operation conditions, and now we can basically use this information as an input to one of the other modules. So for example, for the XYZ, we can say that we run from pipeline, and then basically everything here is filled out, coming from the opt kernel being automatically transferred to this XYZ module. The only thing you can change is the number of points to define the blade here for the only for the cut model. So this is now not used for the computation anymore, where it also plays a role, but here only for the accuracy of the cut model. And now you can run this module, draw the curves, which are now generated. Here you see it's a quite wild model with a high sweeping geometry to, I think, the high Mach number of the velocity and the rather small radius. You end up with something like this, and now you're also able, or I did draw your attention to the fact that we now draw here in between all the different cross sections. So basically this is the discrete model of the wing on which you are computing the analysis, and now you could imagine that starting from there you have this helix-like wake for the other dimension where you sample the velocity field. And now you can also sweep the faces for this model, and if we again change to shaded, you see here that you have a CID model which you can also export. Let's export it here as a step model. Let's call it test. And you can basically use this model in a CID system. So it was written out here. I will throw it into Rhino and show you in a second. Let me just open that, and meanwhile here I will throw in the Rhino CID system. At the moment the model is parsed there, and you basically can see here the generated wing model or propeller model. Oh, sorry, I made a mistake on the handling, and you could probably use this further in some of your analysis. Now you see some effects, for example here which we still have to check out if everything is correct. But yeah, in principle, here you have a full CID model. So far, the hub still missing, the end caps still missing. So this is the XYZ module, the bridge to the CID system. Another thing is the maps module, where you want to see performance maps, which help the engineer to judge how is the performance of the propeller. And also this can be then now run from the pipeline. And yeah, basically you see everything's filled out here, and now we again fire, and it is computed. It also takes a while, so I will again stop the screencast for a second and we'll be back when this is finished. So now that also the maps module has finished running, as you see in the logging, we can hit again plot the maps. Now you see in the previous example where I was reading in existing plot files, we compare two different settings. Here at the moment you have only one propeller, so you're not doing a comparison of two propellers, you have one propeller, and see the different plots for this one propeller. For example, the propeller efficiency comparison for the different pitches, or in this case you should say propeller efficiency plot. And as I mentioned, also sometimes here you have the possibility to change the dimensions from, for example, kilowatt to watts or something. Okay, so this is in principle what we are doing here with this prop design software. I hope you like what you see and you maybe want to give us some feedback. And I will now just make some closing remarks on the strategy of prop design, going back to the presentation. That was the part on the software demo. Now at the finalization of this presentation, I want to draw your attention to two different issues. First of all, there's an upcoming conference called Mecha 2016 in Orlando. The link is given here, and if everything works out, I plan to be there. It is a mechanical and aerospace conference, also with an industrial exhibition. It is in October this year in Orlando, and in general the topics of this conference is aero design, physics, shape optimization, mechanics and robotics. I'm going to be there if everything works out and presenting in a poster form, especially our attempts here to redesign the propeller design code. But not only that, I actually plan, and I hope everything works out as planned, to talk a little bit about using all this tool in the context of the engineering workflow for propellers, also considering some of our other tools, or for example talking about this CID bridge. So for example, how to use this propeller code, but also use it in the context of other numerical tools or other CAD tools, and so on and so forth. This is basically what I plan to present there and talk about. And in case you happen to be around, I would be happy to see you and get active feedback from you about the implementations here and our efforts to modernize the code and write such a software. There's a second thing, which is some other products we develop. First of all, Rhino Rotor Blade. This is a plugin for the software Rhino. So Rhino is a CAD system, and I wrote there a small Python-based plugin which allows you to script the generation of rotors. So what you see down here is actually really a script of a rotor generated by one of the scripts. And the other issue is cooperation with our partner Bell in Bulgaria for CNC machines, so software and also software bridges and interfaces for production machines like CNC, but also for example laser. Very nice stuff. And here I actually used one of these blades to test a bridge for the CNC production, so producing a small example in aluminium. Of course you would say why aluminium, but this is not the point. The point is here really to test the geometry kernel in collaboration with such a CNC bridge. That was the issue here. So you see that here already we are thinking a bit in the future for the software, how we can connect it maybe with some of our other tools like this machine bridges, or bring it also together with things like Rhino plugins and CAD systems. And this is exactly something like an outlook, a strategy on the possibilities there might be. And if I see that this project has interested contributors or people who are interested in having such a code, then yeah, this strategy might come alive, or of course it might undergo some modifications, but in principle, I think it would be very interesting to follow some of those directions. So the idea could be that you have this kernel, for example in Fortran, and now the given interfaces in C and also the geometry kernel with Open Cascade in C++. You can use that to make a standalone GUI, which is what I presented you today. But if you take that and if you, for example, also add a Python interface, which is not there yet, but which I think will be a very nice feature to have, I could think of very nice applications. For example, of course, a very nice integration in CAD systems, so they could directly maybe use the C or C++ interface, but also maybe a Python interface to script some tasks. This is very nice. You could think of a very nice FEA integration, so directly as a plugin that you can directly exchange your models. Also maybe some boundary conditions with a system like, let's say, ANSYS. I just put it here. One vendor, which is very popular, of course, in this field. And as I said, maybe make a real connection to CNC machines for production. That could be something there might be possible, or which could actually be really possible with the interfaces we have now. And if also you have here this concept of having clear defined interfaces, you could place all of that actually in a very nice optimization, multi-objective optimization loop. If you maybe Google for me, you might also find some of my scientific work on Bayesian optimization. So I'm really a fan of this Bayesian optimization. Why is that? Because there you can basically use with different codes like a black box. So let's say you have a multi-objective optimization, so you have to optimize the same time the propeller, where you could use the prop design software to find with the op module a very nice propeller shape, a number of blades under certain conditions of the airplane. But at the same time you have to think of, for example, a production, so there are some other limitations given from the fact that you have to be able to produce the propeller with the given material, and maybe you even don't know what material to use where, if you have a composite structure or something. And at the same time you have maybe some other numerical tools. Maybe you do a more advanced FEA analysis on the propeller to find out something more on the stiffness. For example, the stiffness of the material use, which also influences the production and so on, or even make FEA for the production, because maybe you have a 6-axis machine and you have to know if the propeller is not too thin to be produced in such a machine, and so on and so forth. Yeah, so you have just a really a multi-objective problem. This is typically the case for engineers, and for engineering problems it's rarely the case that you have really a objective function which depends only, or which aims only for one variable, right? But what I really like about this approach, for example the Bayesian approach, is that you could use any of those things as a black box, because sometimes you might not even know, or you don't really have access to some of the things going on there. So you cannot apply maybe something like a gradient based optimization or something, because it's probably hard to determine some of the things there, or to get some information you would need. But you could maybe point-wise compare some issues, or you could know that, yeah, well, the FAA has to show you that you need a certain stiffness of your product, and so on and so forth. So you basically use every of your code as a black box. And if you have clear interfaces, and especially, for example, you have something like Python, I showed in my previous work that it is very nice to bring that all together in such an optimization process. And that would be something I think very neat also for prop design, to place it into the engineering design process, which is then not only consisting of prop design itself, but also bring it together with other tools. And this is also something I think I would like to talk about in the conference. We will see, but if you happen to be around, you could discuss some possible strategies for prop design. Okay, this is now really the end of this cast, and thank you very much, and I'm looking for active feedback. Bye.